So chemistry is universal to all sciences, and what's important here is that the project is due in 2 days for me, and I don't have 2 days. So this chapter is just about the chemical reactions. You know what that is. But if you don't, it's just atoms or multiple substances rearranging themselves chemically to turn into different substances. A real life example is eating rice. God, I love rice. You digest the food by breaking it down to convert it to energy for yourself. Pretty much a chemical reaction is just that, but into an equation form. So the arrow sign is pointing at the products of the thing, so the left side is usually the reactants and the right side is usually the products. And the thing in parentheses is the physical state of the element. For example, gas, liquid, solid, etc. And another important thing that you need to remember is AQ. AQ stands for dissolved in water. Now you may be wondering, why do I need to know this, Tyson? Well, you actually have to balance the equation. And the thing about balancing equations is that you do it because of the law of conservation of mass. And the law of conservation of mass is pretty much that matter can neither be created nor destroyed. So we're going to be using this practice problem right now to really show you what exactly it looks like. Now, if you look on both sides, it's pretty obvious what needs changing here. We're going to add 2 here, a 2 there, right? Make sure everything multiplies together, and boom, the equation is done. So there are 4 types of reactions. There are synthesis, combustion, decomposition, and replacement. Synthesis is just turning 2 reactants into a product. Pretty much imagine two things turning into one thing, like combining. Combustion is when oxygen combines with something else to make heat or light. And I like to think of explosions because I am weird. Decomposition is the opposite of synthesis, where they take one reactant and break it down into 2 products. Again, think of one thing making 2. And there's also replacement. Replacement has 2 kinds. There's single replacement and double replacement. Single replacement is like how your father keeps staying late at work with the secretary. He kind of like swamped out your mother. And if we look over here, double replacement is like the same thing, except for your mother is already hanging out with the mailman for a really long time, and they like to wrestle. So if you look both right here, those both make sense. Alright, moving on to chapter 10, we learn about moles. Now, me personally, I hate moles, but apparently it's really important in this chapter or something like that, so get used to it, I guess. A mole is also known as Avogadro's number. Here's a picture right here. And 1 mole is a unit of measurement for any substance. And 1 mole is equal to 6.022 times 10 to the 23rd power particles. This is any kind of substance, an atom, electron, microwave probably. I don't guarantee you in the last part, but pretty much all elements on the periodic table have 6.022 times 10 to the 23rd power atoms inside of them. Now you may be wondering what this has to do overall, and I'll get to that. Right? And you're not wondering that because you are probably the only person watching, and the only person watching is my teacher, Alphonse. So first you'll need a pencil and paper, and what you want to do is write down the unit that you were given times what you want to find over 1 mole. And the reason why we write it over 1 mole, like a fraction kinda, is so it can cancel out, and then you could divide it across and stuff like that in order to find that one measurement. So I'll explain more in detail in a different equation, right? And when we have more units of measurement, it gets a little more complicated. But right now, this is generally how you do it. Alright, so we're going to be trying this practice problem out. 2.11 times 10 to the 24th power molecules of sucrose. Did I forget to mention that you need a calculator? Yeah, you're definitely going to need one here. So first you write down the equation, right, and everything that you need, how I showed you before, then you cancel them out. After, I divide 2.11 times 10 to the 24th power by 6.022 times 10 to the 23rd power. And remember to put it in the parentheses. Now, me being the genius I am, before when I learned this in class, I did not know that you need to do parentheses. By not know, I mean I was not paying attention. I was completely zoned out, but now I know. So you need to simplify by sig figs. And here we used 2 sig figs. Well, 3 sig figs, because there's 3 sig figs. Alright, I'm pretty sure you guys already know sig figs. You guys got this. And that's how you solve it. Next, what we're learning is molar mass. So molar mass is the mass in grams of one substance. And that's just the atomic mass of the substance. So if you just look on the periodic table, you'll be able to figure out the atomic mass. Now, if you want to find, let's say, how many calories are in 3 ramen packets, then you would multiply 3 ramen packets by the calories amount. Same if you had 3 moles of oxygen, you would multiply it by the atomic mass to find the molar mass. Now, of course, the reverse can be done if you have the mass, but you need to find the moles. Here's an equation, right? and pretty much C would be 1 mole, but C4 would be 4 moles. Oh my god, I'm so tired from those chapters. Let's take a couple seconds to think about life. Never mind, I don't want to think about it anymore. So moving on. Now, chapter 11 is hard because of one thing: stoichiometry. Now, many people find it really hard. I find it as in decently, kind of annoying, and pretty easy to mess up on. But what do I know? I'm just somebody that doesn't even have an A+ in chemistry right now, so. Alright, we're going to start off with oxidation number. So, an oxidation number is the state of its ion charge. Every element on the periodic table has a certain oxidation state when bonded with another atom. So, alkali metals have +1, alkaline earth metals have +2, oxygen group is -1, and halogens are -2, etc., etc. Now, why do they have that certain number, you may ask? Honestly, I'm going to be completely honest here. I do not know. But I searched it up, and that's what my teacher told me, so I guess it's real. Can't deny it. Now, the last thing that you need to remember is that hydrogen changes depending on if it's bonding with a metal or a non-metal, and it changes from being a positive charge to a negative charge. So the next thing we're going to be learning about is the crisscross method. This method is when you take the charges from before and make sure they're at the absolute value of the number. Then you crisscross like so, right here. I'm going to show you what it looks like. Wait, you might be wondering, Tyson, we haven't talked about stoichiometry yet. Well, shut up. So stoichiometry, to sum it up, is the study of mass of the reactants and the products. And it follows the law of conservation of mass, which states that mass can neither be created nor destroyed. And what I like to give an example of this is when you're making rice. Imagine if you had 3 scoops of rice and use those 3 scoops with water to make your rice. Your reactants are 3 scoops of rice and some water, but your products will be a batch of cooked rice which has the same mass of both the rice and the water combined. Now, is this a good example? No clue, honestly. I kind of just thought of this one on the spot, but I guess it makes sense. The next thing we'll learn is mole to mole ratio. Pretty much self-explanatory, the ratio of the moles between 2 substances. It's pretty self-explanatory, but the last thing we'll be covering today is if you need to find the moles of a substance. But the starting substance you get is different. For example, let's say I need to convert the mass or moles of a substance that isn't the substance that we need to find. For example, if I have the moles of NaCl and I want to find the mass of Cl. Now, I'm not going to say how you do it, but I'm just going to show something on the screen because it's really simple. Okay, so nobody gets a break because there is no fun in this video, but chapter 12 is just about precipitation reactions, and let me break it down for you. So recipients are either soluble or insoluble. Soluble as in AQ and insoluble as in solid, which means they don't dissolve. Now, I'm not going to explain this entire table right here. It'll be important to remember. But if you look right here, anything in the alkali metal section, right, combined with any negative ion, will always be soluble no matter what. That's a very important and easy thing to remember. Everything else, it gets pretty simple in the equation. You'll be able to figure it out. Now, this is important because when you do double replacement, which you will have to do eventually, it will swap the elements, and then you have to see if it would become either solid or dissolved in water. So moving on, we'll be talking about complete ionic equations, which are just the particles in a solution. Spectator ions are not in ionic equations, and net ionic equations don't include spectator ions. So if you do have to write a complete ionic equation and then net ionic equation, the spectator ions would disappear from the net ionic equations but stay inside the complete ionic equations. Now, I know that's a little confusing, but you'll see in the example I'm about to show right now how it works. So given this current equation, what would the net ionic version be? Well, it takes the spectator ions out. So that means anything that doesn't make H2O, since H2O becomes a liquid, right? You would take everything that doesn't make it out. And this is what the final product should be. So the spectator ions disappear just like my father. So I would like to take this time out to thank Alphonse for not reporting me to the school, for all the school appropriate jokes I've been making, and how much a great teacher he is. Yeah, so please don't report me to the school, Alphonse. This is all comedic. None of this is true. Now moving on, we'll be talking about mixtures. So mixtures are 2 or more things combining. It's pretty self-explanatory. An example is when you go to, let's say, In-N-Out, you get your drink, and then you decide, I'm gonna use every single drink all in one cup, and it doesn't even taste like anything at that point. There's also heterogeneous and homogeneous mixtures. The difference is that hetero is uniform and homo is not. Let me give you an example. When you're boiling noodles in a pot, does the noodles combine together? No, and that means it's heterogeneous because there's no uniform, and they're also not together. Something that is homogeneous is when it's just water, because water itself is one solid thing that has uniform. Now, the definition of molarity is a little complicated. It's the number of moles of a solid dissolved per liter of a solution, but what I really hear when I hear the word molarity is that it's another equation to remember. The equation for molarity is equal to moles of a solute divided by liters of the solution. Molarity is shown as big M in the equation, and it's pretty self-explanatory. You know what? Stoichiometry is pretty easy. I wonder what's next, though. Why the hell do I still talk? I'm still looking for somebody that loves dipole, and LDF so I can get the hell away from them. But if you love that, then you'll love this chapter at least. Not like you get your parents' love either way. You love LDF. Like, what's wrong with you? You already know what LDF, dipole, pretty much all the intermolecular forces are. But if you don't, I'm just going to go over them real quick. Alright, I'll show them on the screen. Pretty much stronger bonds. LDF is like the weakest bond, I'm pretty sure. You get the point. So let's talk about density, viscosity, fluidity, and pretty much what that means. So the stronger the forces you have, the more dense you are. That means the liquid is more dense since it has stronger bonds than gas, for example, and solid is more dense than liquid since stronger bonds. Fluidity is how much it can flow or move. By it, I mean a substance. For example, water can flow a lot faster than, let's say, honey. And let's think about viscosity. Viscosity is fluidity. It's like fluidity. It's like the measure of strength that resists the flow. Like I said before, fluidity is how easy something like flows around. Viscosity is how hard it flows around. A good real life example of viscosity is that one kid at school, the stuck up one. Yeah, you know who I'm talking about. I'm not gonna point any names, but they can't take a joke. They're really annoying. Like, just go with the flow, man. Calm down. Anyways, I'm just going to show you some pictures of some crystals. So ionic solids are strongest second anyways, and don't tell the other oppositely charged ions that I told you this, but they have the strongest electrostatic forces that exist. I know, crazy. So I'm going to give you a table right now that you have to memorize, sort of. It's not really as important, just look at the stuff from red, just like my teacher told me. We'll be having a test on this later. I am kidding, but I did fail that test kinda. I got 82%. Here's another picture that you have to remember. Pretty much, you already know most of it. The only important thing I'd say that you have to remember is when a solid turns to a gas, right, or vice versa. It's called sublimation when it goes from solid to gas, and deposition when it turns from gas to solid. The last thing we're going to be talking about is phase changes. And you may be wondering what that is, and it's pretty much when a substance changes from solid to liquid. So pretty much the more energy you add, the more motion between molecules is increased. Before we end this chapter, we need to know three things. First, the boiling or melting point of something is higher depending on its intermolecular forces. Second, sublimation and deposition are extremely important to remember, so don't forget that. Third, sublimation is endothermic. Remember that word. It's going to come up a lot later. A good example of sublimation is dry ice. Alright, who's ready for 103 more slides? Oh! I can't do this, man. I can't do this. So chapter 14 is all about gases and freaking laws. If you know me personally, I don't like laws. I break them all the time. So kinetic molecular theory is matter in motion. Yeah, that's it. Because I'm extremely lazy, I'm just going to go quickly over a few things. Gases are small particles with empty space between the atoms, and they have no attraction or very small attraction, just like your parents with each other. Diffusion is moving through another thing, right? And effusion is gas particles moving from one small opening to another. Now, what you want to do is not try to make an example with the balloon, since you'll just end up embarrassing yourself in the middle of class on a Friday. Gas pressure is the pressure built up inside of its container. The faster the particles, the stronger the pressure is. And do you know what ATM is? Now, if you're thinking cash machine, you would be completely wrong because this is chemistry, not a bank, you complete fool. Anyways, ATM stands for atmosphere, which is equivalent to 760 millimeters of Hg, or 1.101.3 kilopascals, but you don't have to worry about the kilopascals part. Honestly, we're just going to be using, I don't even know when we use this, we're not going to be using it too often. Remember when I said we were going to talk about laws? Yeah, we're doing it now. The first law is Dalton's law. Pretty much, it's all the partial pressure in a chemical equation combined. And it can be influenced by many things such as the number of moles, the size of the container, and the temperature. I'm going to be speeding through a few of these laws, but they're pretty self-explanatory in the end. Boyle's law is how pressure and temperature inversely change with each other. For example, as pressure goes down, so does the temperature, just like how in compressed air...
Why is it so cold?
It's because of Gay-Lussac's law, you idiot.
Hey man, not nice.
I don't care, this is my video.
Okay.
So Charles' law is similar, except for it increases linearly, not how Boyle's law increases drastically. I don't know, it's hard to explain, but you'll see right now. But in order to use Charles' law, you need to convert the temperature from Celsius to Kelvin. So again, I'm going to gloss over the combined gas laws. Here's the equation. It's pretty self-explanatory. So STP is pretty much just temperature in gas. I don't fully understand this one, but 1 mole of gas at STP is equal to 22.4 liters. Also, another important thing is ideal gas laws. Ideal gas law is the law for ideal gas. The equation for this is PV is equal to nRT. R is equal to 0.0821 liters times ATM over moles times K. Wait, do you guys remember molar mass? Well, we're bringing it back with even more equations. So much fun! So I'm going to quickly go over the list of ideal gases, and pretty much no gas is truly ideal. Yep, you already know where this is going. We're going to body shame gas.
Yeah, you suck. You're not ideal at all.
So polar gases are gases that don't act like ideal gases. I mean, all gases already don't really act like ideal gases, but this one acts less like it. They actually have strong intermolecular forces, and they take up more space. You guys might want to strap in because we're going to be here for a while. Chapter 15 is one of the longest chapters. Actually, I think it is the longest chapter out of all the other ones that we had so far. And it's pretty much just all about energy. And we're going to be starting off with the law of conservation of energy, which is energy can neither be created nor destroyed. It's also the first law of thermodynamics, but you don't really need to worry about that. And I forgot to mention that energy is also able to reduce heat. And heat is energy flowing from other objects. For example, when you work out and you get hotter because you're using energy which produces heat. So joules. No, not those kind of joules. Joules as in the SI unit of energy and heat. Specific heat is like ramen, like the ramen from before, where the temperature it takes for the water to boil. That's the specific heat. Not all the specific heats are made the same. So some have higher, some have lower. And I'm gonna show you a table right now, but I honestly don't expect you to remember it completely, and it won't be too important because usually in equations they'll give you what you need to know. Calorimetry is simple. By simple, I mean another equation they have to remember. Honestly, this one's pretty simple. It just Q is equal to MC, that triangle thing, and capital T. And what my teacher, Alphonse, my grade teacher, that should definitely give me extra credit for this, said to help us remember as Q equals MCAT, because the triangle looks like an A kind of, and it's like MCAT. You know, it's a lot easier to remember that way. So Q stands for heat. C is equal to specific heat capacity, which is J over Celsius times G, and M is the mass of the solution in grams, and the triangle T is equal to change in temperature. If you weren't already confused, there's a device called a calorimeter. I don't know how to pronounce it, but it's to measure how much heat is absorbed or released during a chemical reaction. So here's a picture of it, and honestly, it's really simple. It's another example with a coffee cup, but don't really worry about it. Remembering equations that you need to cross out like terms, and real quick, thermochemistry is the study of heat changes in reactions. System is the chemical reaction, and the surroundings are the outside things that may be affected by the reaction that you're studying. So there are a lot of examples that we can use. I'm just using this water and ice cube one, but do you guys remember endothermic? Well, it's back, baby, with endothermic and exothermic reactions. This one's really easy and simple. Endothermic is when heat goes into the system and takes from the surroundings. It also breaks bonds, and exothermic is just the opposite of that. So think about when you touch ice, you are exerting your heat onto it. You are getting colder because you're losing heat, but the ice cube is melting because it's taking in your energy or your heat. Alright, so halfway there, guys. Don't fall asleep quite yet. We're going to be talking about enthalpy. So enthalpy is just another way to show heat, pretty much. and the reaction for it is the triangle HRXN. Enthalpy is exothermic reactions because they are always negative, and endothermic is positive. Remember, H is pretty much just Q in this situation, just at constant pressure. So when you're doing the equation triangle H is equal to H products minus H reactants, oxygen gas is equal to 0. So before we get on to the last part and the last law of this entire thing, I would like to tell you, Alphonse, personally, to go outside, touch grass, because this might be the longest part. Actually, I take that back. You don't need to, but everybody else that is watching this video, if anybody actually is, I want you guys to go, walk outside, touch grass, relax, and come back. 5 seconds. It felt pretty good, right? That's great, because this next part is not going to be great. So, do you see this man right here? This is the monster that created this 10-step equation and law. But instead of actually explaining all these laws right here on the screen, I'm going to just be showing you how it's done. And by the end of it, you should just get the gist of how to do it. Here's the equation I found online. What you want to do first is grab a piece of paper with a pencil, because that's what Alphonse told me to do, because you're going to be erasing some stuff. First, you write the equation on top, and then the equation you want to find at the bottom. In this case, it's Ca solid plus 2H2O liquid becomes CaOH2 solid plus H2 gas. So your goal is to make sure your equation total matches that of the equation that you want to find, and then you have to add up all the enthalpy at the end. So first, what you want to do is look at the equation. Imagine everything as a fraction when you stack it up. So we see up here, over here, that there's Ca solid, and is there any Ca solid over here? Yes, there is. Now I would change the H2O to 2 by multiplying 2 to both sides and everything, but you don't do that, and you'll see why right now. So let's move on to the other side. We have CaOH2 on the product side already, and all we need left is H2. But H2 is on the reactant side, and we need on the product side. So what we do is flip it around. So it becomes H2O turns into H2 plus 1/2 O2. And then what you do, since you flipped it, you also have to flip the sign. So the enthalpy becomes positive. You then see that there's 2H2O on both sides. There's a Ca on both sides, on the side that we need. There's CaOH2 on the side that we need. And there's H2 on both sides that we need. So now you can notice stuff that cancels out. For example, the 1/2 O2 cancels out, the CaO cancels out, and everything else stays the same. So now what you need to do is add all the enthalpies together, and what you should get, let me see what I got, is enthalpy negative 414 kilojoules.